Okay. All right. So, well, let me start this course on finite element methods. We have a. I like this actually. This picture a lot. This is real art. This is by an artist in Spain called Rómulo Celdrán, and you see he takes inspiration from photography, but the same applies. It's amazing how remarkable this applies to what I do on a daily basis, right? So you see basically different refinements of a mechanical piece, and then you see that as you refine, in the finite element case, it would be a mesh. Then you get closer to the actual object, and we will do a lot of that. I mentioned already a lot of refinement, and we will see how the approximation gets better and better to the exact solution. This is something that we will study in detail today. Most of you know already finite elements, but you don't know what you have to do to see the error, right? How do you know that the error in the solution is reducing as you refine the mesh, or how much you have to refine the mesh? I'm sure those questions are still in the air. So the course is a course on enriched finite element methods, and so there are many reasons why people started to come up with different formulations. Mainly to address some of the issues of the standard finite element method. Okay, in a way, you have as I said earlier, you have a standard finite element approximation that you are actually enriching, or you are augmenting with another space that hopefully is going to try to solve some of the issues of the standard FEM. So what are the problems where enriched formulations are superior than standard FEM? Because of course every method has its strengths and weaknesses, and so we want to identify what are those problems that we can actually use enriched formulations for. Okay, there are problems that require complex meshing. So imagine you have a complex object, and it requires really heavy meshing, and then you don't want to handle that meshing at all. So in a way, enriched formulations can be used to transfer that complexity from generating the mesh to the formulation itself by means of a geometric engine. I'll show you a bit problems like that. So problems that require remeshing, I have a few here: crack propagation and coalescence, branching, merging, optimization, where you don't actually know the shape of your object, and so from iteration to iteration in the optimization process, you have to remesh your entire object. Moving boundaries too. Imagine you have an interface, solid or fluid gas interface, and that interface is moving with time. And if you want to solve that by standard FEM, that interface has to be remeshed properly with the matching elements. And immersed boundaries. This is also a nice one. There is a lot of research in methods that basically can obtain a solution to a boundary value problem by just immersing an object completely in a finite element mesh. So this originated in fluid mechanics, but there is a lot of these methods being used also in solid mechanics and by the name of fictitious methods. And I'll also show some work on that. So, yeah.
I'm sorry, what does it mean? Immersed boundaries?
Immersed boundaries. So imagine you have an object, yeah, and you want to find a solution to a boundary value problem. That is, so you have your equation, your let's say equilibrium equation and boundary conditions. This forms your boundary value problem, and you want to solve that problem. Of course, one way to do it is to get the object and create a conforming mesh, or a matching mesh. So the sides of the elements are basically aligned with your object. Okay, so if that object is very complex, so creating that mesh may be difficult, especially if you're dealing with three-dimensional problems. And so there is a class of methods that are called immersed methods, or fictitious domain methods, where you can actually take the object and then just immerse it into a mesh. So the mesh is very simple structure, and it's encompassing the object completely. Okay, and of course, it's not as simple as it sounds, because you can imagine that something needs to be done to detect those boundaries. Okay. But there is quite a lot of research on that, and there are plenty of methods. You have CAD-FEM, You have the finite cell method, and there are a few others. So I mentioned already a bit about singularity. So remember that if you want to obtain a good solution, what is a good solution? Well, a good solution is a solution that the error, you can control the error. You know how the error decreases as you refine the mesh. And so if you are, for example, analyzing a problem that has a singularity, then the standard finite element space is not going to give you what you need to obtain a solution that converges optimally. And so this course can also show you how to enrich or augment the standard finite element space with functions that you can actually use to improve the finite element solution to those problems. And then again, problems with localized and sharp solution gradients. So if your function, the exact solution of your problem, has a sharp gradient inside an element, for example, then you know already intuitively that you have to take these elements that are around the gradient and then refine there, right? But if you can actually add a function to the standard space or augment the standard finite element space with a function that has this sharp gradient built in, then you can also improve the approximated solution. Okay, so let's see some problems. Well, the last one is these enriched formulations give you a remarkable property, which is the mesh independency. This flexibility of not being concerned with the mesh at all, right, can be used, for example, to obtain statistically significant results. So you can imagine you have your mesh. Imagine you have, I'll show an example later, but imagine you have a lot of different microstructure realizations, and then you need to obtain some average behavior, okay? And so you can use always the same mesh, no matter what number of realizations you create. And so you can do statistical analysis to get results that are representative for that microstructure, if you will. Okay. So let's look at some of the examples. Flexibility in handling complex geometries. This is what I just mentioned. Imagine you have on the left you have the standard finite element mesh. On the right you have something that you want to use enriched finite elements. So this is just I took this from my PhD work. It's a microvascular network, but the objective for my PhD was basically to design this network. So we didn't know a priori where the network was, right? So we wanted to come up with a way to not to mesh or remesh every single time the network changed a configuration. Of course, I'm not telling the whole story because if you see on the left, we're actually meshing the channels. On the right, that is no longer the case. So some assumptions had to be made, to collapse all those channels to lines. So as long as those channels are slender, then we were able to make that simplification, and you see that it becomes extremely simple to analyze the problem on the right because you are no longer concerned with the mesh anymore. Okay, but there are tons of other examples. All of these are real enriched solutions. Okay, so you have on the top left, you have a propagating crack with the branching. Top right, you have a microstructure containing fibers. And then on the left, at the bottom, you have woven composites. Then you have a microchannel that has a sinusoidal form. And then, well, you name it. You can pretty much do anything. And everything you see here is independent from the mesh, which is really, really powerful. Because take, for example, your microstructure from the top right, and then suddenly you obtain the behavior of that let's say it's a periodic unit cell. You obtain that behavior, and then you want to see, well, what happens if I change the configuration of all those fibers? Well, you can still use the same mesh, and you can do that, let's say 100 times, and after 100 times you obtain an average behavior. So that is the power of these methods that you're going to learn, right? This idea of having a complete mesh independency. This example, for example, this shows enriched formulations being used to propagate a crack. So you see that this microstructure is basically a polycrystalline microstructure, and then you see if you want to propagate that crack and you want to use a standard FEM, well, clearly you have to align somehow the elements are close to the crack tip in the direction of crack propagation, and this is super hard to do. And so even though the mesh that you see on the left is matching to the boundary of the grains, right? The crack propagation in this case has been done independently from it. Of course, a better idea would be to just use a very simple mesh and use that simple mesh also to take care of the weak discontinuity that happens between grains, right? So there is a material mismatch at the interface between these different phases, and so that creates a weak discontinuity, meaning weak discontinuity that the field itself is continuous, is C0 continuous, but there is a jump in the gradient, okay? And so the idea would be, a better idea than doing this would be to just use a very simple mesh and then represent those weak discontinuities due to the interfaces between the materials and the crack also in the same formulation. And later in this course, I'll show you a method that can actually do that very nicely, even though there is a lot of research to be made yet, and the crack propagation part is still not being taken care of. But this is something that can be done with this method that I will show you. Another example of fiber reinforced materials. So Angelo Simone, who was in civil engineering, now he moved to Italy, but he still has a part of his appointment here at TU Delft. He has been working a lot on trying to simulate this type of microstructures. And so you can imagine how hard it would be to generate a matching mesh for a problem like this. And on top of that, to create statistically significant results for this type of materials. And so here I'm showing just the values of the stress at different locations, and he shows that indeed with this type of formulations you can capture the behavior very accurately. This is one of my works in the past. So I was trying to do here to capture the behavior of a microstructure. So what you see here, all those spheres are completely independent of the finite element mesh that if you see in the back planes, if you see those back plane, that is the mesh that I use for the entire microstructure. And then the idea was to obtain statistically significant results, and what you see is that it was just very simple to obtain 10 different solutions and just show the behavior, and you see that most of the differences happen after you have the degradation of the material. So the idea was to investigate what happens to that microstructure when you are actually deteriorating the matrix. So the spheres remain elastic, but if I wanted to have a failure law for the matrix, what happened? And so this is a cool simulation where I'm basically I'm taking this microstructure and I'm applying an in-plane shear strain to it, and then I'm pulling it in mode 1, so in opening mode, and then you see how the failure is distributed in the whole microstructure. And again, this is super simple. Of course, it's not that simple to come up with a geometric engine that does this detection, but once you have that working, then you don't have to deal with any meshing at all. Well, in fracture mechanics, I discussed a little bit about this. If you want to capture the behavior near a crack front, in this case 3D, a crack tip would be in 2D, well, you need to do some special meshing close to the crack tip. In this case, the crack front, what you see here, all these elements, these are called quarter point elements, where these are basically quadratic tetrahedra, where some of the nodes are moved closer to the crack tip. And the reason for that is that you need to do this in order to capture the singularity, the 1 over the square root of r singularity in the stress field, okay, r being the radius. And so some very complicated meshing needs to be done. So imagine if you want to, on top of this, propagate this crack, see what happens with crack propagation, then you have to regenerate this mesh at every step of your simulation and create all these quarter point elements around the crack front to be able to capture the stress field. And capturing the stress field is important because this is basically determining how your crack is going to propagate. Okay? So this is super hard to do with standard FEM. With enriched formulations, you can augment the standard FEM space with some functions that are capturing the singularity, and so propagate the crack that way, because you get a better representation of the stress near to the crack front. All right. Now, what you see here is in my opinion, the most advanced crack propagation simulation. Sharp crack, I'm talking, okay? There are other methods like phase field methods that are able to represent cracks in a smear way over the element, but this is a sharp crack propagation. And for me, this is perhaps the most amazing crack propagation, three-dimensional, of a hydraulic fracture in the world. And this is I got this video from Armando Duarte, who has been working on generalized finite element methods his entire career. He's a professor at the University of Illinois. I don't think there is nothing that beats this at this point, okay, in terms of enriched crack propagation. This is it. Of course, there is a lot of work to be done. As you see here, Armando stopped the propagation of the cracks before they merged. And so there is still some work to be done there, he's now investigating how to coalesce cracks. And these, for example, you have non-planar cracks, and then what happens when they merge. And then he was able to obtain nice behavior of coalescence, which is something extremely hard to do. Okay. Again, I'm referring to sharp cracks, right? Cracks that have a zero thickness. There are other formulations that you can use that are very simpler. They give you a crack representation that is smeared of elements. You can use damage models. You can use the phase field approach. But in the end, to do something like this, where you're representing a crack, is something extremely hard. This is a problem of that requires a very sharp gradient. You are basically applying a moving heat source, and so if you want to obtain the solution using finite elements, standard finite elements, well, you know that you have to somehow refine where you're applying the source, the heat source, right? So as the heat source, if on top of that the heat source is a moving heat source, then you need to remesh, and you have to follow that heat source with your refinement, right? And the solution here is not even standard FEM. It's using something called the P version of the finite element method, which is something that we'll also look into this course. You see that the solution was obtained using a polynomial of degree third order. And so you can think, well, how about we just use enriched formulations for that? Well, you can actually do that, and then you see that you can track a very sharp gradient through that beam, without having to refine at all, because you're actually adding a function that captures the sharp gradient inside those elements. I talked a little bit in the beginning about immersed boundaries. So this is what I meant. Imagine you have an object, you just enclose it, and then you want to obtain the solution. And here I'm just showing you what the geometric engine is creating, right? So I just enclose it with a mesh, and I just rotate it because I want to see what is the behavior, how the geometric engine is dealing with those intersections between the object and the mesh. And I'm not doing refinement, and this is something that has to be very it has to be very it's very important that you guys understand that there is no refinement here. I'm actually using the original shape functions of a parent mesh, the original mesh, and all those little triangles that you see are called integration elements. So those are elements that are created just for the sake of integration, okay? But you are still using the original finite element space. And of course, we're going to enrich that finite element space with something that is able to capture that, discontinuity inside the elements. Okay, and well, a cool example. This is something that my PhD student did. This is the first vibration mode of a beam, and she basically obtained each frame by just rotating the mesh, just just for the sake of fun. And you know, you see that you can capture behavior like this with an immersed mesh. So this is something we're right now doing a lot of research on, and we're almost finishing a paper on this methodology. Something completely new. All right. So these are a few examples of what you will expect to learn from this course. So let's talk about what we will cover. Of course, we are going to. I want to bring everyone at the same level, at least in terms of the standard finite element method. I'm sure you all come with some sort of background in finite elements, but those backgrounds are different. Maybe you just used COMSOL a little bit. Maybe you had a class on finite elements where you investigated the method a bit deeper. The idea is to look at the standard FEM and give an overview of it from the very beginning. So we will look at 1D example first, so that everybody understands the basics. And this 1D example is very important because it will give us a lot of insight into the formulation in higher dimensions. And so you will understand that there is not much difference between analyzing a problem with finite elements in 1D or 2D or 3D. It's the same. Conceptually, it's the same. Okay. After the standard FEM, we will go into the P version of the finite element method. So the standard FEM, basically, if you want to get a better solution, you just refine the mesh. So you get smaller and smaller elements. In the P version of the finite element, you can keep the mesh constant and then improve the approximation of your function. So you can improve the behavior inside each element by, for example, increasing the polynomial order. So instead of using just linear functions, you can use quadratic and then cubic and then quartic and so on to improve the behavior. So this is called the P version of the finite element method. We will look at the extended generalized finite element method. They have different names, but they are essentially the same method. The extended finite element method, the name was coined by the group of Ted Belitsko in Northwestern University, even though it is the same method as the generalized finite element method, which was the generalized DE-FEM was started basically by Babuska and Mellenk, and then by Duarte and Oden in Texas. And so there is really no difference in the formulation. The difference is that in XFEM, it was the first time that a Heaviside function was introduced to handle the discontinuity, a discontinuity for the crack, so that the jump in the displacement that happens within the element. So they introduced this Heaviside enrichment, and then they started calling it XFEM. But the method is the same. We will study these methods, and then we will discuss some of my work. So back when I was doing my PhD, I was one of the people behind this interface enriched generalized finite element method, which we basically proposed as an alternative to XFEM or GFEM to handle weak discontinuities. So if you remember at the beginning of the talk, I said, well, the weak discontinuities are those, if you have a function, your solution is continuous, it's C0 continuous, but then there is a kink in the solution, right? That is a weak discontinuity. So that means that if you take the derivative, if you take the gradient, there is a jump, okay? And so you have many problems in engineering that have this type of description. And you can think, for example, of composites, where the difference in material properties at an interface, at a sharp interface, gives you this behavior in the gradient, okay? And then I will also talk about something super new. This is my new work here at TU Delft. I called it the discontinuity enriched finite element method, and it's basically a new approach to handle both weak and strong discontinuities independently from the mesh. So it's something that came out after the IGFEM, the interface enriched GFEM, and it's basically augmenting that space by another set of functions that are able to represent the strong discontinuities. Strong meaning now there is a jump in the field itself, and you can think about fracture mechanics problems for this. Okay, and of course we will do a lot of computer implementation, right? The idea is that you really understand how the finite element method works, and you have the understanding, you have such understanding that you can actually go yourself and code it and get a solution. Okay, and this is very important for you, because then in the future, then when you're using another tool, then you really understand what's happening behind. It's not a black box anymore, and you know what to tweak in order to get the solution that you want. Or maybe you just continue developing your finite element code that you start here for something else. But you will be able to gather that knowledge throughout this course. So this is it for the syllabus. Many enriched formulations. Of course, we have a overview of standard FEM and also an overview of p-FEM, which are already standard approaches. Well, this is something that we are working on right now. This course is based on the book that we're writing that is called Enriched Finite Element Methods. And well, I mentioned already some of the work of Angelo and Armando. We're working super hard on this book. So hopefully by the end of the summer, we will have a first draft, even though, you know, we're all very busy. And so we're expecting, I think our expectations are a bit too high. But in any case, this will happen, and it's basically discussing the material that I will give you. You will have access to this in the nota bene. You have seen in the announcement how to access this, and I'll discuss a little bit about that later. So let's talk about the course. So the last year I got some review from the Taylor board, right? There were some very nice things said about the course, but I don't want to spend too much time on this. I want to go to what needed to be improved. So I also got some feedback to, hey, what are you going to do to improve this course, okay? So one of the things that was, let's say, hindering some of these students is the prior knowledge, okay? And so that's why I want to spend some time in the beginning of the course to bring everybody to speed, right? I want everybody to be on the same page on what is the standard finite element, so we can take that as our starting point to delve into enriched formulations. The organization part, well, it seems that there is another finite element course happening at the same time, and unfortunately on this I cannot do anything. In terms of the number of ECTS, I heard that the amount of work required for the course was too much, right, for 4 ECTS. And well, even though I disagree, I'm going to do something about it. So the thing is that last year, students had to write from scratch their own finite element code. And that proved to be extremely hard if you had no programming experience whatsoever, okay? So what I will do this year is I'm going to give you a starting finite element code from the beginning. It's going to be very simple, right? But you're going to start with a working finite element code that you are going to take and you're going to analyze, and then you're going to understand how it works, and then you're going to be able to extend it to do all the other crazy stuff that we will do. Okay? So that is one thing that I'm going to do this semester to help you. The other thing that I want to do is, well, there were 2 projects last year, and it seems that there was too much load. So one part was on the programming, the other part was on 2 projects. Even though these 2 projects are still dealing with 1D examples, yeah, I kind of agree that it was perhaps too much. So what I'm going to do now, the 2 projects are going to remain, but the first project you're going to do on your own the same way you did it last year. The second project is going to be in teams, okay? So this is going to be nicer, because then you're going to you're going to take advantage of synergy, and then you know by having interesting discussions with a colleague that you pick, so it's going to be groups of 2, then you're going to be able to tackle this problem. Okay, so I guess that, did I miss something? Deadlines. Oh yes, important. Last year there were no deadlines, and this was a very bad idea. So you can imagine that most people didn't work at all until the end, but at the end they had to do other stuff, and so I'm still waiting for projects today. And so, yeah, and so, right? Okay, and so what I'm going to do now is we're going to have deadlines, right? But at the same time, I understand you're busy, so there's going to be not so harsh, okay? But there are going to be deadlines. Now, going back to the projects, it is very important for me that you do the first project yourself, because this is where you get most of the knowledge. Okay, like you need to learn about convergence rates. You need to learn about how to obtain an approximate value for the exact strain energy of your problem. You need to do this yourself. You need to have a deep understanding on that. Now the second project is going to be more fun. Like you can go crazy. You can come up with a crazy idea and say, hey, we want to do this, and say, yeah, sure, it aligns with what the course requires. Fine, I'm fine with that. Okay, so that's it. I would like to see if you have any questions. I keep touching my computer instead of touching the iPad to go to the next slide. Yeah.
You said the project's going to be 1D.
Yeah. So the question is, if the projects are in 1D, there are basically there are 3 projects. Project number 1 is 1D.
Right.
Project number 2, you have 2 options. One is 1D and one is 2D.
Right.
Now, you can, of course, you can go for the 1D, but you know it's not easy 1D. Okay, it's tricky 1D, right. But it's still 1D. So okay, so I'm basically, if you think about doing something in 1D or 2D, yeah, it's the same. It's just that implementation-wise, you have to do a lot of more work to get it to work in 2D. But the fundamentals, the basics, what you need to know about finite elements, you can all understand in a 1D problem. Okay, in a 1D setting. Other questions? Yeah.
We get the code from you, so I was wondering in terms of intellectual property, after the course is done, what you can do with the code. Can you still use it for yourself? Or?
Yeah, you can use this is going to be freely available to all of you, so whatever you come up with during this course is all yours. Yeah. Other questions? No questions? All good. Okay. So, just in time. We're going to stop here and then we're going to see each other in 15 minutes.